Okay, welcome back to another Physical Sciences 3 lecture. We're going to do this example 5 shortly, but first of all I want to talk about current because it plays a role in that example. So current here, and we give current the symbol I. Current is the rate of flow of electrical charge, how quickly charges move around a circuit. It is measured in amperes, A, and it is a base quantity. Okay, so it's a base SI unit. Direction of conventional current compared to electron flow. Okay, so direction of conventional current I compared to electron flow. So basically, current. It's in bold. That's not a very well written sentence. Sorry, I just read that out. That's not a very well written sentence. So but what it wants to sort of remind us is the current I is taken as the direction of positive charges. Okay, but but we actually know that in many conductors, metals especially, it is the negative charges, electrons, which are actually moving. Okay? So this is what this sentence means. So we want to talk about the direction of conventional current compared to the electron flow. It's actually the opposite. Okay, so the convention of current would therefore be in the opposite direction to the motion of the electrons. Okay, if it were protons that were moving, it would be fine. It would be the same direction. But what we're saying is that in these ones, we have the conventional current is to write it from positive. So this is our positive and this is our negative plate. So we're saying that the current is moving in this direction, but in reality, the electrons are moving in the opposite direction. So if you see here, electrons will move from um, from this way, from our negative to our positive plate. So it's moving in the opposite direction. But I would say that the current, is actually moving in this direction. It's actually a really annoying convention that they set up. If they set it the other way, it would be very handy for us. But we just have to remember that. So even though we're saying we have a positive current, the electrons are actually moving in the opposite direction. Okay. Um, anyway, with that in mind, we'll go back up. No, what I actually want to finish off by saying was current is equal to the amount of charges flowing per time as well. So that's important that we need to remember. So we have current I is equal to coulombs divided by seconds, and they are amps. So coulombs per second are amps. Now we'll go back up to our example 5. We have an electrical heater is connected to 240 volt mains. What is the potential difference across the heating element? Well, potential difference, like I said before, is equal to volts. So it's going to be equal to 240 volts. And we do just say that's V as well. Okay, so if 2 amps flows for 30 minutes, how much charge has passed through the heater? So I, which is our amps, is equal to Q over T. Now, if we want to see what charge is, then charge is Q. So we need to rearrange that. Q is equal to I times T. And remember, T is in seconds, so we have 2.0 times by our time, which is 30 times 60. And that is going to be equal to 2 times 30 times 60, which is equal to 3,600. And charge is measured in coulombs. Okay, so that's quite a lot. How much charge is passed? So how many joules of heat energy has been released in that time? So if we go back up again, we see that E, change in E, is equal to V times Q. So we have 240 volts times by 3,600 coulombs, which is equal to quite a lot, 864,000 joules. That's equal to 864 kilojoules of of heat. It's quite a lot. Okay. So we'll leave the next example for next time.